composition of compounds. So the chemical formula tells us about the composition of a compound. And when we combine that with the molar masses of those elements, then we can get the relative quantities of each element in the compound, which can be a useful number. One way that can be expressed is as a mass percent composition of an element. And so this is a really good thing to remember. This is the general formula for percent. Percent is the part that you're interested in, divided by the whole thing, times 100. So if we're looking at a mass percent of an element, we're going to be looking at the mass of an element in this substance divided by the mass of the whole thing. And maybe this rock is 29% iron, and that kind of rock is 53% iron. Well, if I'm trying to get iron out of this ore, I'd want to use those rocks because they've got more iron in them. So we can calculate a mass percent from the formula of the compound or from experimental data. And we'll do this one in experiment, I think it's experiment 3. Most of the time, we're going to be doing it from a formula. So let's look at this one first. The experimental mass of a compound. So you take the mass of element X, and you divide it by the mass of the compound, multiply by 100. That's great because you measured those things. Here, if I just have the formula and I'm not given any masses, what do? The mass percent does not change if the size of the sample changes. So a bigger sample, smaller sample. I can pick any sample size that I want. I like to choose an easy sample size. An easy sample size is 1 mole. Because what's the mass of 1 mole of the compound? The molar mass. We can calculate that from the periodic table. And in the process of calculating that, we'll also calculate the mass of X in 1 mole. So you can calculate the percent of each element in the compound. And then if you add them up, theoretically, they should be exactly 100, right? But we're not using exact masses, and so it might be 101 or 99%, something like that. That's okay. So acetic acid, HC2H3O2, is the active ingredient in vinegar. Calculate the mass percent composition of oxygen in acetic acid. So we should recognize that this is an acid because it starts with H. And if we cover up the H, that C2H3O2 is the acetate ion. And the 8 becomes ic, and we get acetic acid. So we're looking for percent oxygen. So we want to know how many grams of oxygen in how many grams of HC2H3O2, and multiply that by 100. And we're just going to choose a sample size of 1 mole because it makes things easier. What's the mass in grams of 1 mole of this? Well, we just went over that, right? So we look at this. How many hydrogens are in this guy? There's 4. If you want to put them in separately, that's fine. If you want to do 1 hydrogen and 3 hydrogens later, that'll work too. I'm just going to bunch them together. There's 4 hydrogens times the mass of hydrogen. And there's 2 carbons times the mass of carbon. And 2 oxygens times the mass of oxygen. I'm getting 60.052. And would round that in the second decimal case. So this number is what we're going to put down there. So this is going to equal something over 60.052 grams. What mass of oxygen is in this? 32. It's right there. We already wrote it out. And you can even write it as 2 times 16 up here. Let's do that. So this is 2 times 16 grams. So that's the one, and this is the other. I guess I should be consistent and do this over here, not making a mess. Times 100. So 2 times 16 divided by, bless you, 60.052 times 100. How many sig figs will this answer have? 4. If you're keeping track, which I'm sure nobody is, 3 and 4 are the most common answers for how many sig figs in Chem 1A problems. So 53.29% oxygen. Any questions?
Would that ever be asked like for the ion part, like the acid with an oxygen?
Yes, you could say what is the mass percent of acetate ion in acetic acid. And so then you would want to separate off that one hydrogen so that up here you could have the mass of just the acetate. We don't have to worry about the electron. Acetate has an extra electron and hydrogen is missing an electron. It's so small that we don't have to consider it. Any other questions? Mass percent also works as a convenient conversion factor. So this allows us to convert between mass of an element and mass of a compound. Really, the only time we use this is if someone outside of chemistry gives us the mass percent, and then we can just use that to convert. It's not really worth calculating the mass percent to use it as a conversion factor. The word percent literally means per 100. So when we say Freon 112 is 69.58% chlorine by mass, that means 69.58 grams are chlorine out of 100 grams. So there's the conversion factor between mass of the element and mass of the compound. What mass in grams of iron 3 oxide contains 58.7 grams of iron? Iron 3 oxide is 69.94% iron by mass. Now, we could do this using molar mass, but they gave us the mass percent. And then, the title, using mass percent composition as a conversion factor, suggests that maybe we should do it like that. So, this is a conversion factor problem, dimensional analysis. What are we given? 58.7 grams, and we've got this percentage. And what are we trying to find? Mass in grams of that. We can actually do this without writing its formula. So here again, like other times, they've given us 2 numbers to start with. 69.94% iron is 69.94 grams of iron per 100 grams of iron oxide. I don't want to write out the words iron oxide, so I'm going to write its formula. So when choosing which one of these to start our path from, this is the one that cannot be used as a conversion factor, so we want to start with that guy. And then we're trying to get to, and that's grams of iron. We're trying to get to grams of the iron 3 oxide. How do we get from one to the other? We just use this. Gives us the direct relationship. So sometimes this happens, you're like, oh, I've got a really long arrow because didn't think ahead. So 58.7 grams of iron. This is an example of where sometimes it's important to specify grams of what. Because if I don't write grams of iron and grams of iron 3 oxide, I could easily get it backwards. So it's that many grams of iron. And what I want to find is grams of the iron oxide. So I need to divide by grams of iron. This is the same way we use density as a conversion factor. So I take the number and keep it with its unit, 69.94 grams of iron. That goes on the bottom because that's where grams of iron is. And 100 grams of Fe2O3. Just a note about sig figs. When we say, 69.94%, it's 69.94 per exactly 100 grams. So we don't have to think about the significant figures in there because that's a definition. So 58.7 times 100 divided by 69.94. How many sig figs? 3. I almost wrote percent. 83.9 grams. Any questions? Now, some people are really good with percentages, and you're like, well, I just know what to do with that. That's great. Go for it. But if you don't, this is how you can do it without learning anything new. 83.9 grams. We can also get conversion factors from the chemical formulas because the chemical formulas have relationships between numbers of atoms and molecules or moles of atoms and moles of molecules. So this Freon 12, C2, Cl4, F2. If we're looking at the relationship between carbon and the whole compound, there are 2 moles of carbon in 1 mole of the compound. Or we could write it for chlorine. There's 4 moles of chlorine, that's that subscript right there, 4 moles of chlorine for 1 mole. But these chemical formulas give us relationships in moles, not in grams. So we can't say there's 4 grams of chlorine in 1 gram of the compound. For one thing, that would be impossible. I don't know what the other thing is. Determine the mass of oxygen in a 7.2 gram sample of Al2SO43. What's the name of that? Aluminum sulfate. Aluminum doesn't need a Roman numeral. SO4 is sulfate. We don't need to worry about all those. I almost offended the computer again. We don't need to worry about all these other subscripts because the charges communicate that. If they gave us the percent oxygen in this compound, we could do this problem faster. But they didn't because they want us to use the chemical formula as a conversion factor. So this still amounts to dimensional analysis. where I have 7.2 grams of the sample, and I want to have the mass of oxygen. So I've got 7.2 grams of Al2 SO43. It's tempting just to call him Al. And we're trying to end up with grams of oxygen. What kind of a conversion factor can I get from the chemical formula? Can I get grams of oxygen to grams of aluminum sulfate? No, it's going to tell me moles. So in this formula, how many moles of oxygen are there? 12. So you could think of sulfate as being like a wagon, where S is the red metal box part, and 4 is oxygen is the wheels. Even looks like wheels, right? And there's 4 wheels. And so we've got parentheses around that because it's a unit, and we have 3 of them. So how many wheels on 3 wagons? 12. So there are 12 moles of oxygen in every 1 mole of the compound. So this is the important thing that we need to get from grams of one thing to grams of another, but we need to go to moles in between. So we go to moles of Al2SO43 to moles of oxygen to grams of oxygen. And this is looking a lot like a stoichiometry problem, except we don't have a chemical reaction here. Get that out of the way. So I've got 3 arrows. We're going to have 3 fractions, 7.2 grams. And yes, this gets tedious writing this stupid formula over and over again. Deal with it. Having to retake the class because you failed is also tedious. So, like Dora, we're following the path that we wrote. So grams of that to moles of that. To moles of oxygen to grams of oxygen. And that first unit comes down in the bottom. And this one comes down here. And moles of oxygen down there. Same thing we were doing with feet and inches and meters and stuff. It's dimensional analysis. This is where it becomes very useful in chemistry. And this is not the only place. Okay, do we know any of these numbers? Well, we've got this guy, right, that we figured out from the chemical formula. It's the mole ratio for these 2 guys. So here I have moles of oxygen on the top, and it was 12 moles of oxygen to 1 mole of compound. Over here, grams and moles, that's the molar mass of oxygen. Do I need to consider that oxygen is a diatomic element? No, because oxygen is not by itself here. So it's just oxygen. So we look on the periodic table, 16 grams to 1 mole. And then we have to calculate the molar mass of this mess. So 2 times 26.98. How many sulfurs? 3. And we already established there were 12 oxygens. So 1 mole of aluminum sulfate weighs 342.17 grams. 7.2 divided by that times 12 times 16. How many sig figs? 2 this time. So that would be 4.0 grams of oxygen in 7.2 grams of aluminum sulfate. Any questions?